Good morning, welcome to new lecture. Today I will look at the several problem, truss problem. First I will look at the determinate truss problem. We wanna find the deformation in the truss. Then I will look at the indeterminate truss. One of them we have extra support, in another one we have extra member. To see how we can find that extra support traction or extra member force using virtual work method. This truss, assume we have this truss. A, B, C, D, E, F. Dimension, each one 15 feet, 15 feet, 15 feet. The height for this truss it is 20 feet. Load, external load, we have one external load here, it is 9 kips. Another external load, it is here, downward, it is 18 kips. Cross-sectional area, I'm writing beside of each member inside of parentheses, and unit it is inches squared, so 5 inches squared. 6, 2, 6, 6, 5, 2, 5, and 6 second. And square inch, it is the unit. Young modulus for all members, it is 30,000 KSI. For the following truss, it means this truss, determine the vertical deflection of joint B. We want to find vertical deflection of joint B using virtual work method. We want to find deformation at joint B in the vertical direction using virtual work method. Let's see how we will find that step by step. It is very easy. First, we will look at this truss. Using joint method, you will find internal forces in these members. So we have truss subjected to real load. This is our truss. Under real load, we will find internal forces for each member under real load. So that is easy part. So I will list here member. Member list, it is AC, BF, AC, AB, BF, CD, DE, EF, AD, AE, and BE. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. You will find internal forces for each member under real load. For example, this column we will show with F. If you use joint method, it is very easy. You know from static, you will cut joint by joint. You will start from that joint. You have only two unknowns or two members, and you will write summation of force in horizontal direction, vertical direction. Using two equilibrium equations, you can find two unknowns. Of course, before that, you should find reactions as well. And finding reaction here is very easy. You can find that reactions too. So, first step, you will find internal forces. Internal forces Compression force I will show with negative, tension positive. Negative 10, positive 1.5, negative 12.5, positive 15, positive 15, positive 7.5, positive 18, negative 12.5, positive 10. So I have this truss. This is determinate truss. You see we have only 3 reactions, and it is simple truss. We have triangle. It is stable. It is subjected to external load at nodes 1B, at node B in the horizontal direction, another at node in the vertical direction. I want to find the formation in the vertical direction at joint B. First step, I will find all members force, internal forces in all members using joint method. I will list member. I will find the internal force for each member under real load. Then I will remove these loads. So I will assume I don't have these loads, so you will remove it. You will apply unit load. At the joint you wanna find the deflection. You want to find deflection of joint B in the vertical direction. So you will apply unit load. Load is equal to the 1 at joint B in the vertical direction. So next step, you will remove external loads, real loads, you will remove those. For the same truss, you will apply unit load at a joint of interest. At that joint you want to find deflection. And in that direction you want to find deflection. Here we want to find deflection at point B in the vertical direction. I will apply unit load 1 at point B in the vertical direction. Again, I will find reactions and I will find internal forces in all members under this virtual unit load. If you solve this truss again using joint method, you will find internal forces. You will find this times internal force positive 5 over 12, positive 1 over 2, positive 5 over 6, negative 1 over 4, negative 1 over 4, negative 1 over 2, 0, negative 5 over 12, and 1 over 3. So in this step, we will apply the unit load at joint of interest. In that direction we want to find deformation. Then again I will find internal forces for all members using joint method, and I will write here. Then for each member you will find L, the length of that member, divided by EA. For each member, length of that member divided by E for that member times A for that member. And please pay attention to the unit. So these are fixed, and this is the cross section A. It is in inch square, so you should convert these feet to the inch. This is inch and this is KSI. So pay attention to the unit. Then for each member you will find L over EI. It will be 1 over 500, 1 over 1000, 1 over 500, 1 over 1000, 1 over 1000, 1 over 1000, 1 over 250, 1 over 500, 1 over 250. Then you will multiply these together. It means you will multiply force in each member under real load times L over EI. If you multiply this column to this column, F times L over EI, you will find elongation or deformation in each member under real load times internal force under virtual load. So you will multiply 10 times 1 over 500 times 5 over 12 for each member. So this will be negative 8.33 over 1000. Positive 0.75 over 1000. Negative 20.83 over 1000. Negative 3.75 over 1000. Negative 3.75 over 1000. Negative 3.75 over 1000. 0. 10.42 over 1000. And this one will be 13.33 over 1000. Then you will add all these together. It means you will find summation of F bar, F, L over E, A. That will give us the delta. That will be negative 15.91 divided by 1000. It means roughly, this is equal to the roughly negative 0.016 inch. This will be deflection at joint B in vertical direction. It is negative. You apply this unit load upward. If you find the positive, means deformation or deflection, it is upward. Because you find negative, it means deflection in this truss under those real load will be downward. Let's look at to the next problem. Next problem, we have the same truss, but we have extra support. So we have the same truss, everything is the same, everything. The shape, dimension, cross-section, Young modulus, and even the external load. Everything is the same. This is 9 kips. This is 18 kips. But we have one extra support at point E. So this is point D. Here at point E, we have another roller support. Now, we want to find reaction at that support. Now you see this truss 1 degree is indeterminate because you have one extra support. How many support reaction we have? 2, 3, 4. We can write only 3 equilibrium equations. So 1 degree is indeterminate. So using equilibrium equations, we will not able to find that support reaction. We will need another equation, and we can find that using compatibility equation. Let's see what are the steps and how we can find that. So this is our real truss now. You will do something. First step, we want to find support reaction at point E. It means R reaction at point E. We want to find it. So this is our real truss. First step, you can cancel that extra support. If you cancel that extra support, you will have the truss you had before. And this is determinate. You can find reactions, you can find internal forces. You will find internal forces for this truss. Let's draw the truss one more time here. And here in this truss, you have external load here. You have external load, 18 kips here. And 9 kips here. Now you will find internal forces for each member. Everything is the same, only you remove that extra support you had. So, if you remove this extra support and find the internal forces, first step you should find the reaction. So this will be 9, this will be 10. You know from static how you will find, this is 8. Using joint method, find internal forces. I will write here positive 15, positive 15, positive 7.5, negative 12.5, positive 10, negative 12.5, positive 18, negative 10, positive 1.5. So you will find internal forces. This is internal forces I show with black, and tension positive, compression negative. Then you can find, using these internal forces, elongation in each member. How you can find elongation? In one rod, we know from mechanics of deformable body, force times the length of the rod divided by EA will be elongation in that rod. For each member, force in the member times the length of the member divided by EA of that member will give us the elongation for that member. So because we have internal forces, we know that we can calculate the length for each member, we can calculate EA for each member. You can find the elongation in each member. So, here elongation in each member I will write with red if you calculate it, and I will write in unit of elongation, I will write in unit of 10 times to the negative 3, 10 times to the power of negative 3 inch. So you have number here. In order to find elongation, you should multiply that number to the 10 to the power of negative 3 inch. If you find elongation, you will find negative 20. This means negative 20 times this inch. Positive 1.5, negative 25, positive 7.5, positive 15, positive 15, positive 72, negative 25. So the red shows elongation. This will be positive 40. So positive 15, 15, 7.5, negative 20, 1.5, negative 25, positive 40, negative 25. Red shows elongation times 10 to the power of negative 3 inch. Then I will apply unit load here at the point I want to find extra support reaction. So I remove the support. Now I will apply the real load. I will find internal force under real load. Then I will find elongation for each member under real load. Then I have this truss. I will apply unit load because I want to find deflection in the vertical direction at point E under real load. So I will apply virtual load 1 unit. I will remove the external load, the real external load, and I will find again the internal forces in those members. Let's do that. So the same truss. I will apply virtual load 1. Now I will find the internal forces in each member because of this unit load here. That will be negative 5 over 12, negative 1 over 2, negative 5 over 16, positive 1 over 2, positive 1 over 4, positive 1 over 4, 0, positive 5 over 12, positive 2 over 3. So I will find internal forces under this virtual load. Now if I multiply these loads times to this elongation, black one to the red one, for each member one by one, and I add it, what I will find? I will find the vertical deflection at point E under real load. So here I can write delta is equal to, you will multiply this to the red, this to the red, this to the red. So if you multiply that, and for example negative, negative, positive, 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 negative, negative. So pay attention to the sign convention, and for each member one by one, multiply the black one to the red one, add together, you will find deflection at point E under real load. If you do that, you will find 55.92 times 10 to the power of negative 3 inch, because here we have 10 to the power of negative 3, that comes from here. So that will be deflection for point E at vertical direction. So what does that mean? If we don't have this support, point E will move down in vertical direction, and that deflection will be 55.92 times 10 to the power of negative 3 inch. But we have here support. If we have support, what will happen? That support will not allow that point E deforms downward. Why? Because if this point wants to move down, this support reaction will resist against that with the support reaction force of R, and it will move up point E upward, and that displacement at point E should be equal to this displacement. This is upward, this is downward. The magnitude should be equal. In that case, this point E will not move down or up. It will remain at the same level. This is the way we will find this reaction R. Now, assume we have this truss under load of R. We don't have this external load. Let's see how much point E will move up if we apply that load R. So, next step, you will remove external load, all external load, you will remove it. Instead of that support, you will apply the support reaction R upward, and you will find internal forces in each member under that R. If you do that, you can find internal forces for each members. So the same truss load, this time it is R, apply, find the reaction and find internal forces in each member using joint method. If you do that, you will find all forces in terms of R. 1 over 2 R, positive 5 over 6 R, negative 1 over 2 R, negative 2.3 R, negative 5 over 12 R, negative 1 over 4 R, negative 1 over 4 R, plus 5 over 12 R, this is 0. So this time the load, you have the same truss, instead of this support you will apply the reaction of support. We don't know how much is that, so we apply to something like R. We apply R. Then we want to calculate how much this point E will move up because of this R. That deflection upward should be equal to this deflection downward. So in order to calculate how much this point E will move up, if we apply R, first we will find internal forces in each member because of this external load reaction R in terms of R. I found that. Then after that, we will apply the unit load here. Then we will apply unit load 1 here, this times upward, because we want to measure to see how much point E will move up if we apply R here. That forces I can show here. Let's see. That forces if I apply 1 here upward, that forces will be positive 1 over 2, positive 5 over 12, positive 5 over 6, negative 2 over 3, negative 1 over 2, negative 1 over 4, negative 1 over 4, 0. So, because the first time you apply downward, we apply downward, now we are applying upward, the magnitude will be the same, but the sign will be inverse sign. So let's double check to see everything is right. Positive, 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 negative, negative, negative. So negative, this will be negative 5 over 12. Yes, negative 5 over 12, negative 1 over 4, 0. Everything is, it seems right. So now we have real load this time. We assume real load, it is the reaction at point E. We find internal force in terms of R, that extra reaction at point E. We will apply unit load at point E upward, and we will find again internal forces in truss members. Again, these forces multiply to this force, multiply to the length of each member divided by EI. So this force multiply to this force, multiply to L divided by EI. For EA, sorry, I pronounced wrong. So internal forces in each member times under virtual load 1 times internal force for each member under this reaction R times the length of member divided by EA of each member will give us the displacement upward. So if we do that, we will find the point E. If we apply R here, it will move up 4.486 R. So we will multiply this force to this force times for each member L, the length divided by EA. We can calculate that. Then we will add all together. This member to this member, this member to this member, this member to this member, and so on, times the length for each member divided by EA. We will add all together. We will find the deflection of point E upward in vertical direction. So, now we should plug these equal. From there we can find R. If I put 4.486 R equal to 55.92 times 10 to the power of negative 3. Of course here I should have another times 10 to the negative 3, sorry I dropped this. If I plug this equal, from here you can find reaction is equal to 12.46 kips. And positive means the reaction direction is upward. So what I did, let's summarize it. Whenever I have extra support reaction, first step, I will remove that support reaction. After removing that, for this truss, I will calculate it, the deflection at the support place, at support reaction. How I will do that? I will find internal force in truss member under real load, then I will apply the virtual load at that location, and I will find internal force for each member under virtual load, then I will multiply that load under real load times the load under virtual load times for each member length divided by EA. I will add together, I will find deflection, for example, in this example at point E downward. Because here we had a support, that point E cannot move down. So what we should do? We should apply the reaction, the effect of support. The effect of support means reaction of that support as an unknown R, for example. So I will apply the reaction R. I will remove external load. Now I will find internal forces. Because of this external load, here external load, it is extra reaction R. And then I will apply virtual load here, and I will find again internal forces in each truss member under that virtual load. That internal force under virtual times internal force under this extra reaction times the length for each member divided by EA will give us the deflection at point E upward. These two deflections, they should be equal together because this point will not move down or up. If we put those deflections equal, I will find extra reaction R. Let's look at to the next problem. Next problem, we have the same truss. This time, next step, I have the same truss. This time, instead of extra support, I have extra member. Assume we have one extra member here, and that extra member cross section is again 5 inches squared. So I want to find internal forces in each member. And external load, again, it is the same external load what we had before. Here we have 9 kips, and here we have 18 kips. This truss, internally it is indeterminate. Externally we have 3 support reactions, so we can find support reactions. But because of extra member here, if we use joint method or section method, we will not able to find internal forces using equilibrium equation. So again we will need compatibility equation. Now we have only one member extra. What I will do then? I will remove that extra member. If I remove that extra member, what will happen? I will have determinate truss. So I will find again internal forces in these members. So exactly everything is the same here. So you will remove the external, extra member. You will remove extra member. So you will assume you have the truss what you had before. And here you have 9 kips, and here you have 18 kips. A, B, C, D, E, F. Now you will find internal forces in each truss member under real load. Again, several times we find that. Again, I'm writing -10, +1.5, -12.5, +10, +7.5, -12.5, +15, +18, +15. Then after finding these internal forces, you can multiply these internal forces for each member times the length of that member divided by EA of that member. So you will have elongation for each member. You will find elongation for each member. Again, you can write elongation for each member here. And we did this step before, and again it will be in the unit of inch, and answer 10 to the times 10 to the power of -3. So you will find elongation. Then after finding this elongation, you will find relative displacement of point B respect to the D. To see under real load how much this distance from B to D will increase. In order to find that, you should have the same truss. You should have the same truss, because we want to find to see how much the distance from point B to D will increase after deformation. You will have this truss under virtual load. This time virtual load, because it is relative displacement, you will apply unit load 1, unit load 1 in the direction which attach B to the D. So you will find this direction, the direction B attached to the D, and you will apply unit load 1 here. Now you will find internal forces under these loads. If you find internal forces under these loads, it will be +0.6, +0.8, -1, +0.6, 0.8. So A, B, C, D, E, F. Other members' forces will be 0. Now you will multiply these internal forces to these elongation. That will give us the relative displacement from point B respect to the D. So you will multiply this red elongation times under real load times to the internal force under virtual load. And virtual load, it is relative displacement of B respect to the D. If you calculate that, that will be equal to positive 124.5 times 10 to the power of negative 3 inch. So we find the relative displacement of B respect to the D under real load. This point B distance respect to point D will increase this much. Now, if we have extra member here, what will happen? This extra member, this elongation, this relative displacement will create elongation in this member. This elongation in this member, we can write compatibility equation, because if we don't have this member, the distance from B to D will increase delta BD. Because of that, elongation or the relative displacement of B respect to the D, we will have internal force in this member. That internal force magnitude, we don't know how much is that. We assume it is F. That F will create another relative displacement of B respect to the D. So this is, it is increasement, it is positive. First, because of external load, the distance from B to D will increase. Because of this internal force, the distance from B to D will decrease. So if we subtract from each other, that should be equal to elongation in this member. So next step, what we will do, if I have here, I should have it. Next step, I will remove all external load and I will apply F and F here. If I do that, where I put that page, I cannot find it. I think I don't have that here. But next step, you can find those yourself. Next step, you will remove all external loads. You will have the truss and you will apply force F and F here. So you will assume you have this truss, and instead of this member you will apply the internal force for that member. The internal force that for that member, it is unknown, we will assume it is F. If we apply F and F here, we can calculate again relative displacement of C, D, E, F. We can calculate the relative displacement of B respect to D again. This time, first we will apply F and F. We will find internal forces for each truss member. Then, at the same truss, because we want to calculate relative displacement of B respect to the D, at the same truss, we will apply virtual load 1 and 1. So what we will do, first we will apply F and F. We will find internal force in each member under this load. Then we will apply 1 and 1 virtual load. We will find the internal force at each truss member under this virtual load. Then the internal force under virtual load times the internal force under real load, means this F, divided times the length for each member divided by EA. That will give us the relative displacement of B respect to the D because of this internal force in this diagonal member. Finally, in reality, how we can find this internal force? The relative displacement of B respect to the D will be relative displacement of B respect to the D at first step minus relative displacement of B respect to the D at second step is equal to elongation in that member. Elongation at this member will be force at that member times the length for that member divided by EA of that member. So from here you can find F, because this is in terms of F, this is in terms of F. You will take to this side, you will plug equal to that, and you will find that force F. So one more time I will explain the procedure. If we have extra member, for example, member BD, we want to find internal force in member BD in this truss. If we have one extra member over there, our truss internally, it is indeterminate. We cannot calculate internal forces using equilibrium equations. We cannot calculate using joint method or section method. So what we will do? First step, we will cancel this member. And we will calculate the relative displacement of B respect to the D. So we will remove this member. We will calculate relative displacement of B respect to the D. Then, because in reality we have that member, what is the role of that member? What is the effect of that member? That member applies force, internal force like F. How much is the F? We don't know that, but we can apply as an unknown F. We will apply this F here in that member direction. Again, we will calculate the relative displacement of B respect to the D under this F. That will be delta B D2. Finally, the relative displacement of B respect to the D will be equal to the elongation at member BD. That elongation at member BD will be internal force at member BD, which we assume it is F, times the length of member BD divided by EA of member BD. In order to calculate relative displacement of BD, if we don't have this member, what we will do? We will find internal force in each truss member under real load. Then we will remove the real load. We will apply virtual load 1 and 1 in this direction. We will find internal force at each member under this virtual load. Then real load times virtual load times for each member length divided by EA of each member will give us the relative displacement of B respect to the D at first step. Then minus. We want to find relative displacement of the point B respect to the D under load F. What we will do? We will apply load F like this. We will find internal force for each truss member under this F. Then we will apply 1 and 1 again. In the first step, our 1 and 1, it was in opposite direction. Now it comes together. First it was outward, now it comes together. So we apply 1 and 1, and we will find internal forces in each truss member under this virtual load. Again, internal force under this virtual load times internal force under this F times the length for each member divided by EA will give us delta B D2. So delta B D2 will be in terms of F. That should be equal to, because in reality we have member here, that should be equal to relative displacement of or elongation of this member. Elongation for this member will be force in this member times the length for this member divided by EA for that member. This delta B D2, it is in terms of F. If we take to other side, we can find F, because it is one equation, one unknown, we can find F. So, thank you so much for watching this lecture. See you next session. Bye bye.